Good morning, everyone. Is my voice audible to you?
Yes, ma'am.
Okay. I hope my screen is also visible. It's visible, right? My screen?
Yes, ma'am.
Okay, thank you. Okay, so last class, what we did, we discussed about the sedimentation aided with coagulation part, right? We have discussed about the four coagulants that are used in your the sedimentation process. Okay, so regarding your that one, we have one numerical we have to know. Okay, we will do one numerical. So this one already done in your last semester, but still will have to repeat it. Okay. So like the question it goes like determine the quantity of alum required in order to treat 13 million liters of water per day at a treatment plant where 12 ppm of alum dose is required. Okay, also determine the amount of carbon dioxide gas which will be released per liter of water treated. So what it is saying that you have to find the quantity of alum, okay, which is required to treat a treatment plant where 13 million liters of water is being treated. Okay, so you have to determine the quantity of alum and where also 12 ppm of alum dose is also required. Okay, and also you have to find the carbon dioxide gas. So after seeing the question, your in your mind it should come that it is saying about alum, so that means you have to use the chemical reaction that you got in your the alum equation. Okay, you have to remember that equation. Since I already told that you have to, okay, just wait, some students are waiting. Okay, so since I already told that you have to anyhow remember the chemical reactions, because if any numerical comes, then you have to use the chemical reaction. After that, only you can proceed to your numerical. Okay, so here in this question, similarly here also, you can see what things are given. You can see here that it's given that the what is the quantity of water that is treated in the treatment plant is 13 million liters. Okay, there is million is 13 into 10 to the power 6. Yes, let me annotate it. Okay, so you can see it's written here in order to treat 13 million liters of water per day. That is, it is 13 million, that is 10 to the power 6 liters per day. Okay, and what is the amount of alum dose that is required? The alum dose required is given 12 ppm. Okay, it's written in the question 12 ppm. And what is ppm? ppm is parts per million, which is also your milligram per liter, same thing. Okay, so they have written it with 12 milligram per liter. So now you have to find out like if the quantity of water to be treated is given and the amount of alum dose is also given, then you can find out how much of alum is required to treat the water per day. Okay, so what will you do? You have to just multiply both. Okay, that quantity of water and the alum dose you have to multiply, and you will get the what is the amount of alum that is required to treat the water per day. Okay, that is after multiplying they are getting it here something like 156 kg. Okay, so this is 156 kg is your the amount of alum that is required to treat the water per day. So now you have to use the chemical reaction in which your alum is used. Okay, so this was the chemical reaction. Okay, this was the balanced chemical equation. You have to write the chemical equation. Okay, after that you will find the molecular mass of your alum. Okay, molecular mass of alum, and also in the second part of the question you can see it's given that you have to find the amount of carbon dioxide. So they are asking you what is the amount of carbon dioxide that is evolving. Okay, what is the amount of carbon dioxide that is released. So now you have to find out the molecular mass of two things. One is will be your carbon dioxide and the other one will be your aluminum sulfate. Okay, so that is you are finding the molecular mass of alum. So this is your molecular mass. Okay, this is of alum. You have to find out Al2SO4 3 18H2O. So you have to remember the molecular weight of aluminium, you have to remember the molecular weight of sulfate. So each of the elements you have to remember the molecular weight. Okay, this is somewhat of your chemistry type. So you have to remember the molecular weight, then you find out the molecular mass of your compound, that is alum. Okay, so like aluminium it is 26.97. Okay, then sulfate is it is 32, then your hydrogen is 1, everybody knows, then oxygen is your 16. Okay, so you do the calculation and you will find the molecular mass to be 666. Okay, so now again similarly you find out the molecular mass of carbon dioxide. Here there is, it is a balanced chemical equation, so here it is a 6. So your is this carbon dioxide, it is your 12. Okay, plus 2 into 16, so that is coming your 44. Okay, so now you have to, after getting the molecular mass of alum and after getting the molecular mass of carbon dioxide, so now you can see that this 666. Okay, the 666 amount of alum is it will be used to release how much, to release 44 milligram of carbon dioxide. Okay, 44, or you just multiply it. Here they are writing 6 into 44. You can multiply the 6 beforehand only. In here only you can multiply your 6. Okay, so that means 666 amount of your alum is used, it is used to release your this 6 into 44 milligram of carbon dioxide. So now in the question it is given to find out how much like carbon dioxide will be released if 12 milligram per liter of alum dose is used, right? So if 12 milligram of alum is will be used, then it will release how much. You use the unitary method. Okay, you use the unitary method and you will find out it will release 4.76 milligram of carbon dioxide gas. Okay, so so here there will be two answer. One is your what is the amount of alum that is required to treat the water per day, that is your 156. You are getting one answer, and the other one is how much amount of carbon dioxide gas will be released. So that one is your 4.76 milligram per milligram. Okay, so finally, it's written here. So since 12 milligram of alum is required for treating 1 liter of water, the quantity of carbon dioxide evolved per liter of water is equal to 4.76 milligram. Okay, you can just write the answer as simply as 4.76 milligram. Okay, so this is your not very tough, it's a very easy numerical. You just need to know some basics, like you have to remember the chemical reaction, and also you have to know the molecular weights of each elements, so that you can find out the molecular mass of each compound. Okay, so this one, so the next numerical you will be trying by yourself. Okay, this one, example number 9.13, you try at your home. do this, okay, without seeing the answer. First you try to do, then after that you, if you can't do, then you refer to the solution and you try to do by yourself, okay. Similarly, same numerical, just here the chemical reaction will be of your ferrous sulfate, okay, ferrous copperous, sorry, copperous here it is using, so you have to use the copperous equation reaction, okay. Okay, so this was all about your sedimentation aided with coagulation part. So now we will be coming to the next one, that is the same, this one, the continuation of your sedimentation coagulation itself. So that is your the constituents of a coagulation sedimentation plant. So we have first learned that like in sedimentation coagulation, we are learning that we are adding the chemicals or coagulants, and after that a flock is developed, and that after this flock is developed, the particles settle down, okay, and then it is removed by the sedimentation tank, okay, by the outlet of the sedimentation tank. But actually how these things are happening, these are not happening in a single tank or in a single unit, okay. So all this, like you are yeah, putting the coagulant, then you know, like a flock is happening, then you are again sending those things to a sedimentation tank. So all these are happening in certain different units, okay. So that is here, it is what will be explained in this part, that is the constituents of a coagulation sedimentation plant, okay. So this coagulation sedimentation plant, it is also, you know, like sometimes it is known as your clariflocculator. So somebody if asks you that what is a clariflocculator, so you will have to know that they are talking about the coagulation sedimentation plant, okay. So this the coagulation sedimentation plant, okay, they are having like 4 units. Number 1 is your feeding device, number 2 is your mixing device, also known as mixing basin, number 3 is your flocculation tank or flocculator, and number 4 is your settling or sedimentation tank. Now we will be seeing what are happening actually in all these 4 units, okay. So basically this is you can see this diagram. This diagram is your Dorco clariflocculator, okay. It is manufactured by a company known as Dorco. So it is you, if it is horizontal, you could have seen this, they are having different units, like this is the inlet, okay, then these are like flocculators, these are settling basins, you can see here, these are baffle walls, we will all see. So this is as a whole, this clariflocculator looks like this, okay. As a whole it looks like this, and they all, the different units, they all have different mechanisms, okay. So first of all, what is done is that the chemical coagulant, okay, it is first of all fed into the raw water, okay, through the feeding device. So there is one feeding device, okay. We will again learn it separately one by one. So the whole procedure is like this, okay. First of all, the chemical coagulant, they are added to the raw water through the feeding device, okay, and this mixture, okay, it is then mixed thoroughly, okay, in a mixing basin. So there is a mixing basin. After you add the coagulants, only in the mixing basin it is thoroughly mixed, okay. The water and the coagulants are thoroughly mixed in the mixing basin. Then the flock will be formed as a result of this chemical reaction taking place when in the mixing basin. So a flock will be formed, and then those flock, it will be allowed to consolidate in the flocculation tank. So there is one flocculation tank, and in the flocculation tank of the flocks will be formed, okay. Then this flocculated water, it will pass to the sedimentation tank, okay. So there is one sedimentation tank, so it will be passing to the sedimentation tank, and in that sedimentation tank, these flocculated particles, they will settle down, and it will be finally removed by the outlet, okay. So this is the whole like procedure of your clariflocculator, Okay, so now this they complete this process of this coagulation sedimentation. It is only used to remove turbidities of a value of 10 to 20 milligram per liter. If the water it is having a turbidity of 10 to 20 milligram per liter, only in that case this complete process of your coagulation sedimentation tank is used. Okay, and also it is used in reducing the bacteria from the water, and also it reduces the B. coli index, like it is a bacteria, okay, parameter. So it reduces it to like up to 70%. Okay, so now first of all, feeding device will come. Okay, so feeding device, just now I now told you that in the feeding device what it is done, that you are feeding the, okay, you are putting the chemical coagulant, okay, in the raw water in two forms. Okay, either you can put the coagulant in a powdered form, or you can put the coagulant in a solution form. Okay, so if you put the coagulant in a powdered form, so that is known as your dry feeding. Okay, and if you are putting the coagulant in a solution form, so that is known as your wet feeding. So that means in a feeding device there are two mechanisms. One is your dry feeding and the second one is your wet feeding. Okay, and the wet feeding equipments, they are like somewhat costlier than your dry feeding equipments. Okay, and also they have the advantage that they can be controlled. Okay, they can be controlled also, and they can be adjusted also. But you know, like, whom to choose, whether you have to choose dry feeding, or you want to choose wet feeding. So how will you choose that one? So that also depends upon some factors. Okay, that depends on some factors. So what are those factors? Number one is your, like, the characteristics of the coagulant and the convenience with which it can be applied. So like, it depends upon the characteristics of the coagulant, whether the coagulant or the chemical which you are using, it will clog, or which are very non-uniform in composition. Those chemicals, that like means which clog or which are very non-uniform in composition, they cannot be fed by what? Dry feeding. For example, you can say here that we have the most commonly used coagulant, that is alum. Okay, and alum, you know, it is very fine and it is very uniform in size. So this alum, it can be used, it can be fed by dry feeding. Okay, but whereas copperas, okay, copperas also we have one as an this coagulant. But this copperas, okay, if you put it in a dry feeding form, it will give some trouble, because you know, like, the crystallization or the crystals that are present in the water, it may exchange sorry, it may change with the temperature. Okay, so when change with the temperature, okay, it might turn the water or it into a solid or a sticky mass. Okay, so therefore, you know, it depends upon the characteristics of the coagulant, whether it is uniform or it is non-uniform, or it will clog, or all these things, it will depend. Okay, so next is your number two is your the amount of the coagulant to be used. So the amount of the coagulant to be used, it is also like important. Okay, in choosing what type of feeding arrangement you want to choose. Okay, so if like the coagulant dose is very small, then you can fed it in a solution form. Okay, for accuracy purpose, you can fed the coagulant in a solution form. So next factor is like the cost of the coagulant and the size of the plant. So suppose you are using the coagulant in a plant which is a very big plant. Okay, so in that big plant, you know, like, the cost of the coagulant, it will be an important factor. Okay, so what will you do, that it can be used in a cheapest form. Okay, and the plant this should be equipped to use the chemical in that form. So in a very large plant, the chemicals should be purchased in a cheapest form, and the plant, it should be equipped to use the chemical in that form. And also, like if the plant is small, then the feeding equipment, it doesn't, it like it is doesn't become the the important factor. The important factor will be like the chemicals which you are using. So if the plant is small, you use the chemicals, those are in the dry form. Okay, so these are all the factors like for your feeding devices. So now see this one, all these things are somewhat of a like a practical type thing. So if I go on explaining, you will not understand. So what I want to do, there is one video, I got it in the YouTube. So here they have explained it very nicely. Okay, with all this animation type of thing, they have explained it. So I think you will be understanding if you watch that video nicely. Okay, but as a whole, I have told you that what is happening in a clariflocculator, right? So you have understood the whole process, but you have to see what are the mechanisms, how they are performing. So you have to know that. So for that, I would like to share one video to you. You watch this video, a little bit long video. It might take some time, but then also it's explained very nicely. So first of all, you watch this video, then you will understand.
So in this video lecture, we'll be learning about clariflocculator. It is the treatment plant in which the clarification as well as the flocculation or flocculating of the particles takes place, and this comes into the sedimentation aided with coagulation. So let's start with it. Now, the coagulation sedimentation plant is sometimes called as clariflocculator. It has four parts. Part A is feeding device, Part B mixing device, Part C flocculation tank or flocculator, and Part D is settling tank or sedimentation tank. Now let us learn about each one by one. Part A, feeding device. Now we can do the feeding now what is this feeding device? Basically, feeding of what? Feeding of coagulant, because sedimentation aided with coagulant is basically that we are adding coagulant to the water just so that the particles get flocculated and they get heavier or their size increases, and the settlement is helped with that. So here we are talking about the feeding of coagulant. So there is dry feeding and then there is wet feeding. Now what is this dry feeding? In this we have a hopper kind of arrangement in which the coagulant is put as a powder, and you see this shaking. This is the agitation of the plates. The plates can be agitated. These two side plates that you can see, this one and this one, they both can be vibrated or they can be agitated so that this coagulant, which is in the powder form, can smoothly drop in. Next we have toothed wheel here. As you just saw its movement, it rotates basically, and whatever coagulant powder that falls down here, whatever coagulant powder that falls down here, that is because of this rotation, it goes to the raw water. So this is a rough way how this entire process works. The coagulant in the powdered form is filled in the hopper bottom. Agitating plates are provided to prevent the arching of the coagulant. Arching is basically, that any powdered form, even the flour at our home, when it is kept for a very long time and some moisture gets collected, then it gets a little bit hardened. So it should not be settled there for a long time. Hence, these agitating plates are there, which keeps the coagulant from moving. which keeps it moving and thus preventing the arching action. The dosage to the raw water is regulated or controlled by a tooth, wheel, or a helical screw. Now, this tooth, wheel, or a helical screw, whenever we want this coagulant or in whatever quantity we want, this this can be rotated, and then we can get the coagulant from there. Next, we'll come to the wet feeding device. Now, this is a little bit complicated in just looking, but very easy in understanding. Now, first we'll see the whole setup. Okay, so this is not the whole setup, but just see. Now, this is a tank in which the wet coagulant is stored. Wet coagulant meaning the coagulant is mixed with liquid, and it is basically in the liquid form. Okay, just like how you get some other products which you get in powdered form and some you get in liquid form, something like that. So here the coagulant is in liquid form and it is stored in this particular tank. Now this, you can see here a valve sort of thing. It's not a valve, but it's the level regulator. Now, as and how the level of this coagulant rises, this ball is there which keeps on floating on the coagulant, and it can go up and down accordingly. So, yeah, so now basically raw water is at the bottom. Now, there's this arrangement which we'll see. There's this plug, as you can see, there's a conical plug here, right? When this plug is raised, only then this coagulant can enter here. If the plug is at the bottom and it is closing the entire thing, the coagulant cannot enter the water. Only when this plug is raised, it can enter. Now, the special part about this plug is that if you raise it more, then more coagulant can enter here. So this plug not only stops the coagulant from going inside the water, but it can also act as a regulator that how much coagulant should go inside the water. Now this entire thing is actuated by, now just when that plug is raised, did you see the plug being raised? Just check it again. When the plug is raised, only then the coagulant gets mixed with the raw water. Now what happens if suppose the supply of your raw water increases? This is the supply of your raw water. Now if this supply of the raw water increases, obviously this dosage of coagulant won't be enough. We will need more dosage of coagulant, right? So at that time what happens when the supply of the raw water increases? Did you see here, when this level increased, this level also increased? You see it again. When this level increases, this level also increases, and there is again a floating ball or floating device which also the level is changed. Now this floating device is attached to this pulley kind of a system. When this goes up, here the pulley is actuated, or the pulley rotates. Because of this pulley rotates, and automatically this plug will also go up. So this plug will move up and more coagulant will start coming down. So this entire process is automatic, that when the raw water comes inside and this plug is raised up, I'm sorry, this ball is raised up, it is connected to this pulley kind of system, and this pulley raises up this conical plug. So when this conical plug is raised, more coagulant is fed to the water. So in wet feeding, the coagulant is prepared as solution and is kept in a tank. The coagulant flow is maintained as per the raw water flow, and the level of coagulant is checked using an automated float. So this is that automated float, and this checks the level of coagulant inside the tank. If this is quite more, then we can stop the coagulant from coming in this tank, because it may cause overflow also, right? The inflow of coagulant in the raw water is controlled by a conical plug. So the flow of this coagulant inside the water is controlled by this conical plug. As the raw water supply increases, the level in float chamber also increases, which elevates the level of the float, which in turn initiates pulley mechanism, and the conical plug is lifted so as to allow more inflow of coagulant. So this is nothing but the same thing which I explained you previous. Let us move to part B, which is the mixing device or mixing basin. Now, after you have put the coagulant inside your water, that coagulant has to be properly mixed inside the water, right? So, first we allow that mixing through a mixing basin. This is the plan of that mixing basin, and here you can see I have drawn it in a 3D shape. So when the flow happens, it has to go through these walls, and automatically the coagulant is mixed. These walls are called as baffle walls. This is a horizontal type of flow. There is also a vertical type of flow in which the water will enter from here. So this is a vertical type of flow, and all these walls are called as baffle walls. So in this, our coagulant is mixed inside the water. Again, we also need something called as mixing device, in which it is mixed with paddles, that we'll learn later on. So this is that mixing paddle which I was saying. This is called as mixing basin or a flash mixer. Mixing basin with a flash mixer. Now let us see how this works. The raw water that just came from those baffle walls, it goes from this end. There is something called as deflecting wall, and we have impeller shaft and impellers. Now what happens, see, when the raw water comes here, it is deflected by this wall, and it has to go down. It has to go from here to fill it up. So it has to touch this impeller. Now these impellers are in constant motion and very fast motion, right? So because of this fast motion, the mixing basin is mixed with a flash, mixed very quickly, or with a flash mixer. Now before this, you can keep that mixing baffle walls which we just saw, or you can also directly put the raw water inside this mixing device or inside this mixing basin. So not necessarily you need to have that baffle wall type of arrangement, horizontal or vertical flow arrangement. Now I hope you understood how this is working. The inlet for raw water will come here. This deflecting wall will make sure that all your raw water comes in contact with this impeller, so that it is mixed thoroughly and only it gets filled. Then this coagulant pipe is there, which will give it constant uh, constant coagulant supply, so that the coagulant is also supplied to the water, and the mixing also takes simultaneously. And then from this part, the water goes up, and it is next it goes to the flocculation tank.
Hey everybody, it's Tony Robbins. How are you doing? It's a crazy question to ask these days, isn't it? Because everywhere I go, literally, and I'm traveling around the world, but I'm doing it mostly through Zoom these days. In a typical year, I would go to 118 cities, 16 countries, and now I'm doing it all through Zoom to meet people. And I'm reaching out to you today because I don't want to see anybody that I can have an impact on suffer. There is so much uncertainty in the world, and the world's about to open.
Coagulant supply, so that the coagulant is also supplied to the water and the mixing also takes simultaneously, and then from this part the water goes up, and it is next it goes to the flocculation tank. The impeller speed is generally kept between 100 to 120 rpm. Now this is important as far as design problems related to this mixing basin is concerned. Detention period is generally half a minute to 2 minutes. The detention period is very less in this kind of mixing basin. Power required for flash mixer may vary from 2 to 5 kilowatts per cubic meter per minute. Power input in mixing and flocculation is frequently expressed in terms of temporal mean velocity gradient. This is something new, where G dash is equal to P upon mu V raised to half, or it is basically square root of P by mu V. Now what is P? G dash is velocity gradient. P is power dissipated in watts, that is Newton meters per second. Mu is dynamic viscosity of water, and capital V is volume of water. Always remember capital V is volume of water. Many times students get confused that that is the velocity. It's basically volume, not to use the velocity. Now what is this G dash? G dash is nothing but the velocity gradient, that is the velocity of particle at this level to the velocity of particle at this level. If I have to draw a graph, let's say the velocity of particle at this level is this much, and the velocity of particle at this level is this much, then the slope of this is nothing but your velocity gradient. Okay, so it is a difference between the velocities at this point and this point, or between any 2 points. You can see between any 2 points, between either this point or this point, the slope of the velocity is nothing but your velocity gradient. Okay, for rapid mixing, the product of G dash into T, which is now one thing that you need to see is velocity gradient. The units of velocity gradient are per second, that is G dash units are per second or second inverse, so, or it is like 1 by second. So if you multiply this G dash with time, you will get a unitless quantity. And for rapid mixing, the product of G dash into T should be around 30,000 to 60,000, where T is the detention period or mixing period, usually 60 to 120 seconds. So for mixing basin, the detention time is around 1 minute to 2 minutes. If not even in the question, we can assume the detention time, or generally it is given in the numericals. Design steps.
Okay, the design steps are not required. Okay, so let me. The meeting will end in 5 minutes.
For
Okay,
mixing
so
basin, the detention time is around.
I am just skipping the design part. Okay, I guess in this video, it's only about the design part. Okay. Okay, so you have seen there till your mixing part, right? So after the this one thing, the solution is mixed. Okay, after the flock it is formed, then your due to this mixing, okay, due to the thorough mixing, what will take place? Your flocculation will take place. Okay, so the flock will be created in the next step, that is your flocculation tank. Okay, so the flock will form, and after that this flock will be carried to the sedimentation tank, and in the sedimentation tank, due to the formation of the tank, due to the formation of the flock, it will settle down, and after that it is removed. Okay, so that is the later part. So it is happening in the flocculation tank, and after that in the sedimentation tank. So that is the whole process of your sedimentation coagulation plant. Okay, I hope the video is clear with you. I think it was explained very nicely with the animation part. Okay, anyways, um, so this was all about your sedimentation aided with coagulation. Okay, so next class we will be going to filtration. Okay, on Friday we will be learning about your filtration process. Okay, so who have given message? Rupashri. Okay, okay. So we will meet in the next class, and about the attendance you message me in the WhatsApp group. Okay, our physiochemical WhatsApp group, you message me your enrollment IDs. Okay, your attendance. Clear, everyone?
Yes, ma'am.
Okay, so we will meet on Friday. You may leave the meeting. Okay, thank you.